Okay, so welcome everybody. So today we'll be giving you the same presentation I gave in San Francisco this year at the DAC conference. So this work is actually an ongoing work, and what we presented was ARCANE, which is more or less a smart IP. It is a smart last level cache. Which you will see it is also capable of doing computations. So this work is done jointly with the ESL laboratory at EPFL, and it is mainly brought on in the VLSI laboratory in Politecnico di Torino. So I get started. So we already know that companies and almost everyone is trying to run machine learning workloads on common microcontrollers. But what we often see is that we very quickly hit the von Neumann bottleneck. What is the von Neumann bottleneck? It's basically a limitation that is actually limiting you from doing correctly consuming your power budget, because what you see is mostly that if you go for very standard and very basic, like the best case of machine learning workloads, which would be vector addition, what this C code does is basically a set of load and store instructions for retrieving the data and storing the data. And then we have a bunch of increment that are basically housekeeping instructions for incrementing pointers. And just one single instruction out of all of this is actually performing the addition among the two vectors. So this quickly actually shows how we can saturate our power budget and how the energy contributions are coming, where the energy contributions are coming from mostly. So they are coming from loading and storing data from the data cache and from the repeatedly fetch of instructions from the instruction cache. So in order to be able to run machine learning workloads on edge devices, we need to rethink the way we are actually doing computation. And if you're here, of course, in this webinar, you know where I'm going to go basically with my discussion. But so we don't want like ASICs, we don't want small GPUs or vector machines because they are fixed. Although they are efficient, they are fixed. And what we know from the ML world is that hardware is actually suffering from very quick obsolescence of IPs, because the ML workloads are changing day by day, year after year, but we cannot cope. The hardware designers cannot cope with this rapid change in the software stack. So we need some way that is more configurable. So when thinking of a way that is much more configurable, first of all, we went to near memory computing, because of course it is decreasing the energy contribution regarding the loading and store of data, because now computation is happening inside the memory, so we don't need to fetch the data from and store it again to the memory. And we in this way we actually are also trying to equip the memory with some vector processing units such that we can run vector workloads. However, the problem with near memory computing is that the programmers, which usually are not aware of how the hardware is composed, will face what we call data management challenges, which actually wrap up the word headache. Because being not aware of the hardware, you cannot, of course, use it so easily. And you need to be aware of many stuff when you're dealing with near memory computing that actually make it less favorable for adoption. And that is why often nowadays we don't see many near memory computing IPs in the market. Also, one step further, we did so we thought, okay, if we already have a data cache in our system, why don't we, instead of teaching how to do the math to our memory, we teach to do it to our data cache? The data cache, in fact, has one strong advantage, that is that it already knows where the data is stored. So it already has tags, it already can match where data we need for doing computation is placed within the cache lines. In this way, we can actually have a faster retrieval for the operands, And then we can perform, of course, and this will impact our computations because we can, of course, retrieve faster the operands and we will be faster in delivering the results. So with this smart data cache, that will be actually Arcane. So Arcane is a fully configurable data cache. It is a last level cache in our system, and it is fully configurable both in software, and we will see why, and in hardware. Of course, you can tune whatever you like to, so the set associativity or the number of vector processing units you have inside, for instance. And while executing, it doubles both as a data cache and as a matrix coprocessor. So from the host CPU, you can offload instructions to Arcane that will be computing, doing matrix multiplication or whatever you like to. And at the same time, you will be still capable of accessing data while you are doing computation. So the host CPU is not blocked while you're doing computation. It's not stalling, waiting for the end of the computation, but it is capable of running other stuff in the background. And also, one key aspect of Arcane is that it provides you with an easy programming experience, and soon we will see how we can achieve this. So what is shown here in the bottom right is what Arcane is actually. So we have taking the standard SRAM banks that would compose the cache lines of our data cache, and we rethink them as vector register files. But they are actually not register files, because otherwise they would increase the power consumption. They still are SRAM banks, and then we do some manipulation in the addresses, in the way we address them, so that when we want to run computation, we can read from them as vector registers. Then we equip each of the now called vector register files with a set of configurable vector processing units. And then, of course, inside this system, we add some more components, among which we have the smaller embedded CPU. So this small embedded CPU is the orchestrator of the system. It is in charge of receiving instructions from the host CPU through the extension interface, which is a standardized RISC-V interface for ISA extensions. And this embedded CPU will receive the instructions, will decode the instruction, and will be then able to run the vector process, the instructions, and will send the vector instructions to the vector processing units. So among the statistics from Arcane, of course, being a near memory computing solution, we have decreased energy contribution in loading and storing data. And also we are decreasing the fetch of instructions energy contribution, because with a single instruction, which is a complex matrix instruction, which will be a matrix multiplication, a convolution among two matrices or whatever, will be with just a single instruction, we are wrapping what will be like the pointer increases that I was showing before. And in this way, we are actually decreasing the energy contribution from that. And also, the data management challenges that we usually see in the near memory computing APs are not present in Arcane, because our ISA wraps out all of the complexity and allows you to use it in a very easy way. Let's see. And soon I will show you how this is possible. So the data management challenges are actually decreased when compared to other near memory computing IPs. Because let's suppose we want to offload a machine learning workload. Let's call it like a generalized matrix multiplication. Then the host CPU will offload the instruction through the extension interface, and then Arcane will decide from this embedded CPU actually will decide on which vector register file run the computation. So it will choose that vector register file, and that one will be used for running computation. So all the vector registers will be used to compute the matrix multiplication. Whereas the vector register files that were not chosen for computation are actually operating as a standard data cache. And so you see the ones that are actually blue, they are not being used at this time for running the matrix computation. And so this is what's happening under the hood. So we have a cache table, which is more or less a standard cache table you would find in a standard data cache. But this cache table has, among the status bits, some more bits that are actually helpful for us to determine whether a vector register is actually being used for computation, and therefore it is not accessible from external loading and store of instructions. Then inside our data cache, we have our finite state machine. The finite state machine is basically capable of handling the loading and store, the incoming load and store requests. So it is capable of doing that, retrieving the data from the cache lines which are not marked as busy computing, and responding to the host CPU, such that the host CPU in the meantime can run other computation. However, the problem is this. So what happens if the host CPU, which is running a workload that is parallel to the matrix multiplication, in the end wants to access the result from an ongoing matrix multiplication, and still we are not done with the matrix multiplication. This will cause, of course, a data hazard if we would allow the host CPU to do so, because of course we would see data that is not yet being produced. So to mitigate this problem, to actually resolve it completely, we add another module that is the address table. The address table is basically checking whether the incoming load and store addresses from requests from the host CPU to Arcane are actually hitting within the address table. So if we have an address that is falling within these ranges, then that load or that store word will be blocked, which means that the host CPU will not see a response from the data cache, and therefore the load store unit from that host CPU will be stalled, and so on. So we are actually, in this way, we are actually granting synchronization between the host CPU and the running kernels without having an explicit instruction to do so. So the host CPU won't be idling or repeatedly polling for Arcane to be done, but it simply will try to access the data, and as soon as the data is able to be fetched, then those ranges will be removed from the address table, and then the request will be replayed, and therefore the host CPU will receive a response. So everything is very transparent from the programmer under this point of view. Then inside our data cache, we have a two-dimensional DMA. The two-dimensional DMA is helpful for us because in this way, the embedded CPU that you see within Arcane is capable of programming it so that we can move the matrices from the memory or from within the cache in a way that is amenable for the vector processing units, so that they can fetch all the rows from a matrix, for instance. In this way, we are very fast in reshaping the matrices within the cache without wasting too many clock cycles. And all of these modules are actually composing this smaller module that is the cache controller. And this cache controller is more or less interacting with the embedded CPU, because they need to coordinate to handle the whole operation of the data cache. So you can think of the cache controller being able to in charge of handling all the requests from the host CPU that are memory requests, whereas the embedded CPU is actually in charge of handling the kernel offload, so the instructions offloading. So it will be able to run and to execute the matrix kernels, basically. So I was mentioning that there is this embedded CPU within the data cache. So this embedded CPU is actually executing some code within this small memory here. This is a very low-level code, and it is what we call the cache runtime. So the cache runtime is built in a modular way. It includes several modules inside, and it is what gives us the possibility of having an extendable software-defined ISA. So what we mean by extendable software-defined ISA, we mean that the kernel, the decoder, so I was mentioning that you can offload instructions to the data cache. Of course, in standard accelerator, the decoder would be some fixed hardware module, and therefore you cannot extend it. But having the kernel decoder within a piece of software actually allows you to reprogram the software, to reprogram this cache runtime with whatever instructions or whatever ISA you want. And in this way, you will be able to always extend your ISA, redefine it, whatever your application is. And also, our software-defined ISA tries to hide all the near memory computing complexity by giving basically two instructions that we will see now. And the instructions are the one you see in the snippet of code. This is actually how you interact with Arcane. So this code is actually being executed on the host CPU. So here we are supposing we want to run some kind of kernel on Arcane. So we have the A, F, and R matrices. And what we do first is to reserve those matrices. What is the reserve instruction doing under the hood? Is basically filling the address table I was talking about previously. So in this way, you are locking those address ranges such that you don't need to worry about the synchronization mechanisms. At this point, whatever kind of access you want to do on these addresses will be logged. And this will be actually done in a transparent way. So you basically, the CPU will be stalled and you don't need to have explicit synchronization primitives. So that makes the code more readable. It makes Arcane also more programmable because it's very easy to launch a kernel on Arcane. And eventually, after you are doing all the reservation for the matrices, you can run the matrix kernel. And since we want to minimize the energy contribution from repeated fetch of instructions, this kernel must be complex. So you have here what we developed as kernels that are useful for TinyML tasks. We have generalized matrix multiplication, max pooling, 2D convolution, several an attention layer, or even a convolution layer, which will be our case study today. So before going to look at the performance of Arcane, we also tried to measure what is the overhead you get from having this, so from bringing computation within a data cache. So we first synthesize XIP, which is an open source microcontroller developed in EPFL. And then we synthesize Arcane on a commercial 65 nanometer technology. And what we see from the results and under this configuration, which gives us 4 vector units in the 4-lane configuration, we actually have just 30% overhead on the overall area. And if we take a look at the split up of the area that we have inside Arcane, we see that the overall 20% of the overhead is due to the embedded CPU control that we have within our data cache. Whereas most of the overhead that we see within the data cache subsystem that you see here is actually coming from the 4 vector units that we have embedded inside Arcane. So of course, the vector processing units are carrying on most of the logic, and in this, and therefore they will of course impact a bit on the overhead that we see. And the cache controller, which is including the address table and the DMA, and the cache table I was showing you before, is just occupying less than 4% of the whole data cache subsystem. So moving on to the performance evaluation. So you might be wondering at this point, what is the overhead of having a cache runtime? So a piece of software or an embedded CPU orchestrating everything. So we are used to having control units orchestrating everything inside our accelerator, but at this time we have an embedded CPU. So we need to understand what is its impact on the overall performances. And we take as a case study this convolution layer. So remember, we are offloading the convolution layer with a single instruction from the host CPU that is computing this convolution, max pooling, and ReLU all within a single instruction between 3 matrices. So here we have an image of the cache runtime, and here on the right, we have what is the overhead split up, so the computation phases split up for the whole kernel execution phases. So they are normalized, and on the x-axis, we actually have the same kernel, but with increasing data sizes. Of course, when using Arcane, we want to place ourselves on the right-hand side of this plot, but we brought this comparison with very small kernels for fairness. So we see that the preamble phase is just comprising the software decoding part. So that is what we actually gives us what gives us the software extendable ISA is actually dropping to less than 3% when we increase the matrix input sizes. And this is actually telling us a strong hint and a strong insight that is that we are not actually paying that much the capability of having a reconfigurable, a runtime configurable software ISA. Then moving to the allocation phases. So the allocation phases are basically those phases where we are moving data with our DMAs within Arcane, so to put data in the matrix shapes so that we can run computations using the vector units. So that allocation phase often saturates at 50% because it is proportional to the input data sizes. Then we have the write-back phase, which is the phase where we take the result matrix and we write it back into the data cache, such that the host CPU can retrieve it quickly when it needs. And this write-back phase is just 2% on the overall computation. And eventually we are left with 80% on the overall time with computation. So we are not hindering too much the throughput achievable by Arcane. So we are not increasing that much the latency we see from Arcane. When taking a look at the performances from the convolution layer, so we did an experiment comparing to a standard CPU and the RISC-V core implementing the pulp extensions. And we do this in several configurations. So NM-Caros is actually the name of the vector units that we are using. And we use it in 3 different configurations. So there is the 2-lane, the 4-lane, and the 8-lane configuration, which is the most performing one. And what we see from this plot is that when increasing the data sizes, we are actually not saturating the throughput that the vector lanes can give to us when we are in this most performing configuration, of course, which means we could actually go for higher kernels, so for greater input sizes. Also, one thing that we can notice is that we obtain very high speedups, both compared to the RISC-V core and compared to the standard CPU baseline. So the speedup achieve up to 50 times more for this workload. And what we see is that, of course, going to a lower bit width in computation means that we, of course, have more throughput because we can compute 2 or 4 times more the data that we will do in standard in32 workloads. So I want to summarize now what we have seen, because it was a lot of information. So I presented Arcane, which is basically a replacement for a system last level cache that comes with matrix coprocessor capability. And it increases the area in a 65 nanometer technology between 20% and 40%, depending on the number of vector units you want to stick inside the data cache. And you pay this small overhead by paying this small overhead in area, you get on average 30 times faster speedups than using a traditional system with a standard CPU, of course. What is actually going on in the Arcane development? So we are working on introducing a feature that is called the auto-tiling, which is almost complete. Basically, the auto-tiling feature allows you to run a kernel with whatever sized matrices. So let's suppose you have a 1000 by 1000 matrix multiplication by 1000 by 1000. So in standard accelerators, you will need to think a lot about the tiling, use whatever you want framework that helps you with the tiling. With Arcane, again, this does not happen. So the tiling is handled by the embedded CPU, which is this orchestrator here, and you can basically issue the instruction and forget about everything. You will gather the results and everything is hidden to the programmer. So this again holds promise to what we said, being an easy programming interface and giving an easy programming experience for whoever adopts this solution. And of course, we are working on writing a mapper that is actually capable of mapping complex workloads such as arbitrary deep neural networks, which will be doing image classification, vision transformers, whatever, onto Arcane so that it is ready to be used. So you put in your ONNX for describing your network, and then you will get the application compiled, and then you can just launch it and get the results, and that's it. So with this, I'm done with the talk. Here you see the emails of me and my colleague which work on the project. So you can, of course, ask me questions now, but you can also reach to us by email if you want to open up a collaboration. We really like to collaborate with others on this topic. So we are really open into that as well. So thanks a lot for paying attention to the talk. Now I'll accept any questions.
Subscribe the channel to get the instant updates on our webinars.